Okay, couple things before we get started, and I guess they're all sort of related. There'll be a new homework assignment for those of you in class. I just passed it out. For those taking it online, you can get on the web page and download it. Normally I give 2 weeks for this, but I'm giving you 3 because I'm going to be gone this whole next week. Including next Tuesday. I'm going to get back like really late next Tuesday. So next Tuesday, for the last time this semester, I promise, it'll all be online. Okay, so next week's class will be online. And then after that, we're going to go back face-to-face through the end of the semester. But because I won't be around this week and because I won't have email, I'm going to give you an extra week to do this, okay? This assignment requires access to a geologic map, which I've put over in the side of the classroom over here by the sink. It's the Masonville geologic map. I am assuming for this exercise that you guys know how to do geologic cross-sections. I also know that by assuming you know how to do geologic cross-sections, that's only true for some of you. Some of you did it in physical geology. Some of you have done this in structural geology. It's something that's typically covered in introductory courses, but I realize that not everybody may have had it. It's not the most difficult thing in the world, but it does take time. It's kind of a time-consuming process. And on your assignment, I've put on 3 links to YouTubes that do a really good job of going through how a geologic cross-section is constructed. So basically, a geologic cross-section has 2 parts. It has a topographic profile, which shows you what the topography does from one point to another. And in your assignment, I tell you I want a geologic cross-section that runs from one point to another point, okay? So you'll construct a topographic profile first, which shows what the topography looks like. You should see areas where it goes up to mountain peaks and areas where it goes down to river bottoms. So there'll be some undulating topography. But what is different with a geologic cross-section is that beneath that topographic profile, you will show what the rock units are doing. And you're going to get that information from the geologic map. If you haven't done this before, like I said, it's not the toughest thing in the world, but it does take a little time and you will need a little instruction. So I've attached several links to help you go through that. I'd like you to look at them if you don't remember how to do it. Even if you do know how to do it, it's probably worth looking at. If you're still confused after going through this, we can set up a Zoom meeting one-on-one where I can walk you through, or I can meet you here in the classroom. Once you have the geologic cross-section done, you should be able to answer the rest of the questions fairly straightforward, okay? It's going to require you to look at the different rock types, figure out which might be confining layers, which might be good aquifers, how deep they are, how far down you have to go to drill to get them, things like this. So this is hopefully kind of a real-world exercise. People have loved it and hated it both at the same time in the past. It's more work than this assignment that you just did. Not by a lot, but the cross-section does take a little time. Once you have the cross-section done, the lab itself, homework itself, is not terribly difficult. Okay, so I'm going to have it due 3 weeks from today instead of 2. Give you an extra week since I won't be around to answer questions. Don't, really, I say this all the time, but seriously, don't put this one off till the last week, because that's like the last week of classes, and all your other stuff's going to start coming due too. You don't want to have this on top of all your other things, so get a jump on it. I only have 15 of these geologic maps. There are 19 of you in the class, so you can't all take them home for the entire time. To do this requires some space, okay? It's probably best to do it here, okay? So reserve some time, come over, do the homework assignment in the classroom if you can. If you really need to take it home, you can take it home for a few days. Email me and let me know that you've taken it home. It's on the honor system, but I don't want to see these maps disappear. You don't want to deprive future groundwater classes of this glorious exercise that you're about to do. So don't steal the maps or I will be really upset. We use them for a lot of different things, a lot of different classes. So try to use the maps in here. Even if you're an online student, come in and do the lab in the classroom, okay? If you have to take it home, you can take it home for a day or two. Just email me and let me know that you have it. Okay, so this is due in 3 weeks. Maps are over there. Do the lab in class. If you do take a map home, email me. Next Tuesday, we will have online class only. And then after that, we will have face-to-face the rest of the semester. Do you guys have any questions? Awesome. Okay, so last week, we had an online video about Darcy's Law, and I'd like to go through that again, kind of cover what we talked about. So Darcy's Law is kind of the fundamental principle that we use in groundwater. It's used a lot in the oil industry. It's a series of experiments that shed light on how material flows through a porous medium. And these experiments were conducted not quite 200 years ago, but some time ago. And it basically consisted of a tube that Darcy would fill with various things, different kinds of soil, different ratios of sand to silt to clay. And what he found is that if he pumped water into one side under constant pressure, okay, so he just had a pump, he turned it so that it was a certain pressure. As long as this material was porous and permeable, there would be some water that would come out the other side. And that's what is denoted by Q. There would be some flow rate that would come out the other side. Now, if this was sand, a lot of water would come out the other side for a given pressure. If it was clay, it was barely a dribble. If it was gravel, it'd come gushing out the other side. So different materials allowed water to move through that tube either more efficiently or less efficiently, depending on the size of the pores and how connected they were. If he turned up the pressure, the flow rate would increase for all porous materials that he put in the tube, which makes sense. Pushing water through it more forcefully, more is going to come out the other side. But he also noticed that if you made your pipe bigger, a bigger cross-sectional area A, more water would come out the other side. Some materials, like sand and gravel, transmitted water much easier. That is represented by our K, which we will get to in a minute, the hydraulic conductivity, which varies from sand to clay to mixtures of sand and clay and silt and gravel. And the other thing that he noticed is that he looked at how the pressure changed in the tube by putting a couple of little ports on the top of his tube that allowed water to roll up inside of them. And he saw that there was a head differential. On one side, pressure was a little higher, head was a little higher. The other side, pressure was a little lower, head was a little lower. Remember, things always move from areas of high pressure to low pressure. So in this case, H1 is higher than H2. Pressure on the left side of the diagrams, higher than the pressure on the right. So material moves from left to right. If there's no difference in head, then there's no impetus to push the material one way or the other. If the two heads are equal, then there's going to be no flow at all. The flow just stops. So let's define the terms that I have here. We have K, which equals the hydraulic conductivity. It's a measure of how easily a fluid flows through a porous medium. As Darcy found out by using different types of fluids, he found out that K was related to both the porous medium and the fluid. So sometimes he would keep the material in the tube the same, but change the liquid that he would pump through. Instead of water, maybe he'd pump through petroleum. And the Ks were different depending on what was in the tube and what fluid was being pumped through it. Now in groundwater, we use water. So we can kind of take the fluid out of the equation. And for groundwater studies, the hydraulic conductivity really just related to the nature of the rock and soil that the water is flowing through. But again, this is a more broadly used law from time to time. So if you're using it in petroleum, you have to adjust for the different viscosity and density of the petroleum product. The units that we use for hydraulic conductivity are length over time. So it's a similar unit to velocity, length being meters, feet, whatever, time being seconds, so it would be like feet per second or meters per second. So it's similar to velocity, but it's not the actual velocity. Because remember, water isn't going to move unless you have a pressure differential in your tube. So you can think of it as kind of what's the potential movement of this if there is a pressure differential. So again, it's similar to velocity, but not the actual velocity, because the actual velocity depends on whether there's a pressure differential or not and how big it is. So not the actual velocity of groundwater movement. And it's probably worth noting here, since this is the next thing we will discuss, is that Darcy's law breaks down. It's not valid if the flow through the pores is turbulent. So if any of you in any of your other classes dealt with turbulent flow before? Anyone?
Talked a little bit about it in second year.
Did you? Any other classes where you've covered it? Well, let's cover it. It's not that difficult. So this is just sort of a little sidebar here. When fluid flows, it moves through one of two different regimes, and we call this laminar versus turbulent flow. Now, in sedimentology, you can get different sedimentary structures depending on whether your water is flowing turbulently or laminarly. In groundwater, if the fluid is flowing in a laminar fashion, then Darcy's law is valid. But if it doesn't and flows turbulently, and Darcy's law is not valid. So we can think of, let's say, a couple of different streams on a slope. The green sort of represents the bottom of the stream. I don't have a brown, I would use brown. Here's the water sitting on top. Water's obviously going to move downhill. But in a laminar flow, the water tends to move along sort of straight, well-defined, parallel flow paths. So this is the laminar case here on the left. And probably the best way to describe it is that the flow occurs in parallel straight lines. But over here on the right, when you have turbulent flow, the flow paths are all contorted. And you get eddies and backflow and a real mess. So for the turbulent case, the flow paths are contorted. So turbulent laminar flow has been studied quite a lot by fluid dynamicists, and they came up with a mathematical way of figuring out which of these two possibilities you're going to get depending on a number of different factors. And the easiest way to define which kind of flow you're going to have is through something called the Reynolds number. And it's just a quantity you can calculate pretty easily that relates to the mode of flow, whether it's laminar or turbulent. Let's just write it out. RE So it's the density times the velocity times the channel opening diameter over the viscosity. So let's look and define these terms. Density. What do we use for units for density? You can just give me one. What's a good unit for density? Think about what density is, and then you should be able to work your way down.
Kilogram per meter squared out of density?
Density is the mass per, it's how much mass is in a volume, right? In a space. So we can do kilograms for mass, and we can do something like meters cubed. It could be grams per cubic centimeter, but we'll keep it the MKS system here. Velocity. What units do we use for velocity? I know you guys know this. Meters per second. Diameter of an opening. Diameter we measure as a linear distance, or meters. And so I don't have to switch page. I'm going to put viscosity over here. You might not remember this one so easy. Viscosity is a Pascal second. which is also a kilogram over meter, second squared. So take a second and tell me what the unit is for the Reynolds number. Meter second. All right, there's a lot of ways you can go about that, but let's look at what we have on the top here. We've got meters cubed on the bottom, meter squared. We can get rid of that. So on the top we have kilogram over meter second. What do we have on the bottom? Kilogram over meter second. Those can cancel out. And we end up again with one of these dimensionless variables. Okay, so it's easy to calculate, but what do we do with it, right? So we find the density of our material. For water, that's typically about 1,000 grams per cubic meter. Velocity is something you would need to know. Diameter is something you would need to know. And you need to know the viscosity for water, which is something I can give you here in a second. And you can calculate the Reynolds number. But then what do you do with the Reynolds number? Well, as it turns out, observations of open channels, like riverbeds, show a transition from laminar to turbulent flow when your Reynolds number jumps up and exceeds 2,000. Okay, so if you calculated the Reynolds number for a stream and you got more than 2,000, it would be flowing turbulently. If it was less than 2,000, it would be flowing laminarly. So it's really easy to use for open channels, okay? But we're looking at groundwater. This is going to complicate it, actually quite a lot. And the reason that it's so difficult to use for groundwater is that we don't know the diameters of the pores in rocks very well. I mean, what is the diameter of the average pore in a sandstone? That's tough to measure, okay? It's really tough to measure. So the problem is that the pore diameter for groundwater use is very difficult to measure. Well, groundwater geologists have figured out sort of a workaround for this. What they did realize from sedimentology studies is that grain size of sand, clay, silt is somewhat easier to measure. We know how big the average sand grains are. We know the average size of silt. We know average size of clay. So we have measurements for the grain size. And in general, the bigger the grain size, the bigger the pore. If you think about how gravel would stack together, they would have much bigger openings in between than little tiny silt particles or clay particles. The bottom line is that by substituting, and I'll give you a chance to use this in a minute. So by substituting grain size instead of pore size, they figured out that laminar flow exists when the Reynolds number, now using grain size instead of pore size for D, is less than 1. So, let me give you an example. Let's say we have a sand aquifer. With an average grain size .05 centimeters. Half a millimeter. So the sand aquifer has fresh water flowing through it. The density of this fresh water should be right around 1,000 kilograms per cubic meter. This particular water measured 999. And the viscosity, and this is kind of a standard measure of viscosity for water. I don't expect you to memorize it, but most groundwater folks do eventually. Is 1.14 times 10 to the minus 3 gram per centimeter per second. The question I'll ask you, what is the maximum velocity of groundwater movement for which Darcy's law is valid? So take a second and think about how you'd use the equation to figure this out. Yes?
Can it equal 1?
Well, so laminar is anything less than 1, right? So if you solve for the velocity when the Reynolds number is 1, the maximum velocity would be anything less than that, right?
Yes.
So that's one good way of doing it, yes. I mean, I guess you could put in Instead of 1, you can make your Reynolds number 0.999999999, and you're going to get the same answer. So use 1. And the maximum velocity is anything less than that. Or I guess the maximum velocity is just barely less than that. So yeah, solve RE equals density, velocity, diameter now of the pore space over viscosity where it equals 1. And you are going to want to solve for that. And of course, your units are going to be all sort of messed up because I gave you some in centimeters and some in meters and some in grams and some in kilograms. And so you have to deal with all that, but you should be good with conversions by now. So over on the right side, I put the conversions for viscosity and diameter. And then you plug it in and chug away, and anybody get an answer? I'm guessing you got an answer, but you might not want to share the answer. Well, I'll put what I got. Velocity should be in meters per second. So is that a fast velocity? .28 times 10 to the minus fourth meters per second. So it's moving a pretty tiny amount every second, right? But if it moves any faster than that, then Darcy's law wouldn't be valid. Any questions on the math? Any step along here you guys aren't seeing or having trouble with? I'm happy to take some time if you are not getting the same answer that I have up here. Okay. So, Darcy's law describes movement through material that has pores. It's only valid if there's laminar flow. The way you determine if something is flowing laminarly is to calculate the Reynolds number. Normally for a stream or some sort of open channel, doesn't have a bunch of rock and debris in it, your Reynolds number transition between laminar and turbulent is 2,000. And it works that way for groundwater too, but it's really hard to measure the pores in a rock sample. But we spent a lot of time studying grain size in rock samples, so we know those a little better. So we can modify this Reynolds number by swapping out grain size in place of pore size. And when you do that, the Reynolds number shifts so that the transition now is at 1. Anything less than 1, it's flowing laminarly. Darcy's law is valid. Anything over 1, it's flowing turbulently. Darcy's law is not valid. So in most Darcy equations that you use, and we'll do some later in the semester, at the end of using Darcy's law, you always have to go back and make sure that Darcy's law was valid for that problem. You need to go through and calculate the Reynolds number to make sure the water wasn't moving too fast and not violating the mathematics of Darcy's law. So this is actually a pretty important step. Most of the time in groundwater systems, Darcy's law is valid. It's really unusual to find a situation where it's not, but you still need to check. Okay, so most of the time you don't have to worry about this, but you should just take a minute or two and do so. Okay? So we'll take a few minute break. Take an 8-minute break, and then we're going to do compressibility of aquifers, which is actually kind of fun. The math is pretty easy. And it can tell you an awful lot about how rocks and groundwater respond to people sucking water out of it.